Okay, we are back. It's 9:18. We are starting reading this paper. We just picked the paper at 9:15, I believe. Mitigating application resource overload with targeted task cancellation. This appeared at SOSP, right?
Yeah,
SOSP in Korea recently. Okay.
yeah,
I
yeah. Last
mean,
la last month, fresh off the press.
okay, Alexi, do the honors with abstract. We have
Okay,
quit.
yeah. So, modern software inevitably encounters periods of resource overload, during which it must still sustain high service level objective (SLO) attainment while minimizing request loss.
Mhm.
However, achieving this balance is challenging due to subtle and unpredictable internal resource contention among concurrently executing requests. Traditional overload control mechanisms, which rely on global signals such as queuing delays, fail to handle application resource overload effectively because they cannot accurately predict which requests will monopolize critical resources.
Mm.
In this paper, we propose Atropos, okay, an overload control framework that proactively cancels the culprit request that cause severe resource contention rather than the victim requests that are blocked by it.
Nice.
Um,
How do
uh,
you identify it, right?
yeah, that's. I think that's the meat of it, right? It's supposed to be. Atropos continuously monitors the resource usage of executing requests, identifies the requests contributing most significantly to resource overload, and selectively cancels them. We integrate Atropos into 6 large-scale applications and evaluate it against 16 real-world overload scenarios. Our results shows that Atropos maintains the performance goals while achieving minimal request drop, significantly outperforming state-of-the-art solutions.
Hmm. Can job cancellation have side effects? I believe you think
Uh,
it can have side effects, right? It can make your caches go bad.
well, like,
Maybe not
I,
not immediately.
it depends, right? So, obviously, it picks the jobs to cancels based on some property of those jobs, right?
Mhm,
So, like in
mhm,
this case, it will pick the jobs that contribute the most to the resource,
mhm,
overload, right?
mhm,
So that means that, like I think in theory, it's possible that some jobs, when the system is overloaded, will be, you know, killed off more often than others, right? So that means that the system kind of, by definition, right, because it deprioritizes some work, it's not fair,
mhm,
right?
mhm,
So if you have a class of jobs that always, for example, high resource usage, right, then
mhm,
this class of job, will be the one that doesn't get done when there is a resource contention.
mhm.
Right? Which, can be a problem, obviously, right? Like if this class of job is something that you need internally.
Yeah, right, right. What if this was about fixing the database or system and you
Mhm.
killing it off? Uh, yeah, you could have a live log kind of situation there. Okay.
You can have a metastable failure.
Yeah, next column. So introduction starts there. Modern software is designed to maximize the utilization of available resources and deliver high performance. However, running a system near peak throughput makes it vulnerable to overload, where a short spike in demand can lead to large number of SLO violations. A classic consequence is the receive live lock, where the system is busy processing incoming requests and cannot make progress in completing pending requests. I didn't know about the receive lock. What is it? 38. It cuts off in the place.
So
38 is the eliminating receive live lock in an interrupt driven kernel. 97. Okay.
yeah, I mean it's a like a classical problem in like operating systems, right? Like the interrupt-based operating system. So if you have,
Mhm.
things that cause interrupts, right? Like you need to, handle the interrupt, right? But if you're already handling the interrupt and another interrupt comes in, you have to stop handling the interrupt to handle the interrupt. Right,
Mm,
so the act of receiving the stuff, in this case, interrupt, it has a priority over finishing the previous, interrupt handles, right? So you can end up essentially in a situation where you're like building this, you know, list of things that you still need to finish because more interrupts come in, at a faster rate and you can, yeah.
Besides receive live lock, overload can also be caused by contention on application level resources such as table locks or buffer pools in a database. In these cases, a single request may hold a resource for a long time and block other requests requiring this resource.
Mm.
Such resource overload is difficult to mitigate because one request impact depends on the subtle and unpredictable interactions with others. This unpredictability is exacerbated by the variability in how different requests access resources in modern systems. For instance, a short single row update query might lock a table for only 2 milliseconds, whereas a long group write request could hold blocks on multiple tables for hundreds of seconds. Consequently, a single long-running write query may cause much more severe overload than hundreds of shorter requests combined. Yeah.
Mm-hmm.
But what did this paragraph say? I got it was wordy and I got like
Locks, right? If you run in long and hold the locks, everyone is waiting on your locks, right? So
no resource overload difficult to mitigate because the impact of request is unpredictable.
well, I guess like if you start killing off the tasks that are waiting for a lock, right?
Mm,
You're actually not making any more
yeah.
progress, right?
Oh,
Because
yeah.
you're not unblocking the system. So I think what they say is essentially you need to, kill the task that, causes the blockage.
Well, hopefully releasing the lock in the in the process. If you kill
Well,
it
yeah, yeah, yeah.
in the lock. Okay, you go.
So the okay, existing overload mitigation strategies fall broadly into two categories, shown in
Figure
Figure
one.
1.
Let's look at figure one. Okay, performance isolation, overload control. I know the setup paper. It's a 2002 paper. Uh, it's yeah, admission control queue. Okay, the others are similar to it, and this is like SLO attainment, higher SLO attainment,
Mhm.
but lower in preserved requests because it kills requests. Whereas the other is higher in preserved requests, but lower in SLO attainment. Who would want that? Uh, resource container, P-box, performance isolation. Interesting. Hmm. I guess it makes them keep going, even though it
Uh,
makes
yeah, yeah.
slow progress. It makes everything keep going.
I mean, like these are two different classes of
Hmm.
performance management like systems, right? Like you want performance isolation, for example, again, like in the database, right? You may want to isolate different queries, or in multi-tenant systems, like different tenants and whatnot, right? So that yeah, like you keep going, or you cannot get more resources um than your share, right? But sometimes actually like that may hurt you, right? So again, like if you have this like a long running query that is blocking a lot of stuff and you're giving it a lot of very little resources because of the performance isolation, right?
Mhm.
Then everything waits. But maybe if you can give it more resources so it kind of finishes quickly, right? So you can, you know,
Okay,
yeah. Anyway,
let's keep
where we are.
figure one.
Yeah, figure one, admission control and performance isolation. Admission control mechanisms favor throttling incoming requests or reducing load. These approaches assume the overload is caused by total demand. They perform
Mhm.
poorly under application-level resource overload due to the lack of insight into individual request behavior. As a result, they often indiscriminately drop many requests that are victims of the overload before they are served at all, instead of specifically targeting requests that are culprits of the overload.
Interesting. I mean, what do you mean culprits? Why are they culprits? They are just taking longer time, but
Or,
maybe
or, or
they are
taking more
very
resources,
critical.
right?
And maybe they are critical, and we gotta wait them out. Okay.
Mhm. Yeah. The indiscriminate drop of requests severely damages application usability. On the other hand, performance.
Is that so? I mean, mm, I think applications are used to getting resource not available signal and adjusting for that. Maybe even that would help them
Well,
have
well, well, you know,
load
to,
go away more.
to a degree, this obviously somewhat exaggerates, right? Because
Mhm.
this indiscriminate drop of requests,
Mhm.
only happens when you already like overloaded, right? So it essentially happens in situations you want to avoid in the first place.
Yeah.
Right. So, so,
Mhm.
so, the stuff that we're discussing here in this paper is kind of, I want to say, second line of defense, right? Like you, in the first place, don't want to get into the
Yep.
situation where you overloaded.
Sure.
When you overloaded, you need to deal with it, right? So that's a second line of defense.
Yeah.
So how often do applications actually um, get severely damaged because of this? That's, yeah.
Mhm. Okay, now,
Uh,
on the other hand, performance isolation allocate resource quotas for each request. The static resource partitions cannot adapt to highly variable workloads, leading to low resource utilization and high tail latency. Okay, it looks like it's like a TDMA-like thing, giving.
mhm. These limitations raise the following research question. How to enable applications to maximize SLO attainment under resource overload while minimizing request drop?
Mhm.
To address this question, we design Atropos. I'm sure I pronounce it differently every time and every time incorrectly. An overload control system whose core principle is to actively identify requests that monopolize the resource and cancel those requests rather than deny requests that are victims of the resource overload.
Yeah.
Atropos does not perform admission control directly, but aims to maximize the chance that the request is admitted and served, and focuses on ongoing requests instead of pending requests. It monitors the overall application resource usage and the resource consumption of each executing request. When a resource is about to overload, Atropos identifies and cancels the request that, if canceled, would release the most load on the contended resource.
Mm.
Right. So look here, when they talk about resource, it's not just like CPU or memory. It's log
Yeah.
contention, anything, right? Like I think it can be like physical and logical resource.
Mhm. Interesting. But like cancellation may also have the cost, right? Like if you are scanning big thing, you are paging and prefetching. When you cancel, you are also wasting a lot of work that was already done for this, and
Yep. Yeah.
maybe
Yeah.
even
So like yeah,
losing
like
performance as a result.
if you have started
Hmm.
some heavy requests, right?
Hmm.
And it has run for long enough, definitely
Yeah.
canceling that is the waste, right? Um,
I
yeah.
was also thinking about like, can this break the system's momentum and make it a almost cold start because you are canceling and the
Mm.
cost of cancellation could be even worse or something. Okay, let's keep reading. We will understand more, I
Mm.
think. Atropos provides two abstractions to simplify estimation of resource overload. First, it groups all application activities, both request and background tasks, into individual cancelable tasks, which are units of work that can be canceled. It attributes resource usage to these cancelable tasks. What is cancelable task? Are they requiring something from the system, from the system to tag things as cancelable task, or maybe program this way in terms of cancelable tasks?
Yeah, good question. I don't know. Like
Mhm.
to me, like for example, if you have a query, right, like everything that is related to this query execution is this one task, right?
Mhm.
Even though it may not be done, I don't know, maybe in sequence or whatever, right? So like
Mhm.
anything that's related to this particular thing is one task that you somehow need to cancel. So I think it's just like all the activities related to something, logically same, right? Like
Mhm.
a query or I don't know, maybe like index rebuild task or clean up. I don't know.
A second, Atropos provides an application resource abstraction that unifies a variety of resources Enabling resource agnostic cancellation policies. I don't know what this means. Enabling resource agnostic cancellation policies. Each application resource exposes two performance metrics. Interesting. Contention level, a measure of resource contention, and resource gain, which estimates how much load would be freed by canceling a given request.
Mhm.
Atropos continuously monitors resource usage. When resource overload is detected, it proactively cancels the task that offers the greatest resource gain to quickly elevate contention before end-to-end performance decreases significantly. Mhm. Okay, we have just two things. Interesting. Okay, Alexei.
While providing general support for canceling and executing requests safely is challenging due to diverse and complex cancellation logic in each application, our study reveals opportunities to enable safe request cancellation. We analyze 151 popular applications and find that 76% of applications already implement custom cancellation logic to safely terminate ongoing requests. Our study further shows that most applications follow a common cancellation design pattern.
Okay,
They
hold on.
expo
Wow. First of all, like 151 popular applications analyzed, that's a lot of work. And
Have you seen how many authors in this paper?
looking at if they have custom cancellation logic, still a lot of work.
Mm,
They expose a cancellation initiator to trigger the cancellation. What? The applications.
yes, yes.
This.
So the mechanism is some kind of trigger, a cancellation, some kind of cancellation initiation to trigger the cancellation. This observation inspires us to hook Atropos to the existing cancellation
Mhm.
initiator functions in each application to perform cancellation safely.
Yeah, let's keep reading.
Yeah. Um, Atropos aims to provide a general resource overload control framework applicable to diverse software. We implement Atropos for 3 programming languages, C, C++, Java, and Go, and integrate it into 6 widely used large applications. MySQL, Apache what?
Uh, I don't know.
All of Apache projects?
I don't know.
Apache something.
Apache is not an application. Yeah.
PostgreSQL, Elasticsearch, Solr, and etcd. To evaluate its effectiveness, we reproduced 16 real-world application resource overload issues and compared Atropos with Protego, a state-of-the-art overload control mechanism, PBox, a request-level performance isolation framework, and Dark, a request-aware scheduling framework. Our evaluation shows that Atropos outperforms all 3 systems in the evaluated cases. Atropos sustains 96% of the baseline throughput and keeps the 99th percentile tail latency within 1.16 times compared to the non-overloaded case.
I
While
mean, this
dropping,
is amazing, right? Mm-hmm.
yeah,
Dropping fewer than 0.01% of requests. Like, what is that? 1 in 10,000? Wow.
yeah, yeah.
I mean,
I, I want to see.
even in the overload, just sustaining 96% of the throughput, that seems magical. Okay,
Well, yeah, yeah.
I'm hooked. We can. In summary, this paper makes the following contributions. We propose a novel overload control mechanism based on selective runtime request cancellation, enabling effective mitigation of resource overload. We develop Atropos, a general and resource agnostic framework that proactively cancels culprit requests to mitigate application resource overload. We demonstrate the practicality and effectiveness of Atropos in 6 complex large-scale applications across 3 programming languages. Good. I think it's clear.
Mhm.
It's a good introduction. We know what we are expecting, no mysteries.
Okay.
And maybe the bad news is no mysteries. it works well. I mean,
Well, well, okay.
one mystery for me is how does it work so well?
Yeah, the mystery is like if you're really overloaded, how does removing 0.01% of requests like
Mhm.
actually helps you, right? Unless this is such a massive resource hogs, right?
Yeah, looks like applications have that thing, and maybe this comes with some sort of a survey about categorization of tasks, and maybe it will say that the task that we end up canceling turned out to be this type of scan tasks or something.
Mhm.
Let's read. Cool. Uh, your turn.
Uh, okay, background and motivation. Application resource overload. Application resources are logical abstractions defined by an application. These resources typically encapsulate underlying system resources such as memory or synchronization primitives to provide high-level application-specific functionality. To concretely discuss the challenges of mitigating application resource overload, we present two real-world case studies of application resource overload in MySQL.
Hmm.
Case 1, buffer pool overload. MySQL's InnoDB storage engine maintains a buffer pool to cache table and index to accelerate query execution. However, when this buffer pool becomes overloaded, it can trigger trashing, where MySQL spends a lot of time evicting and loading pages between the buffer pool and disk. Yep.
Classic.
This buffer pool contention is further complicated by the fact that different types of requests consume varying amounts of buffer space, making it difficult to predict the performance impact of each
Well,
request.
this is what I'm talking about. When you are in such a crunching situation or trashing situation, how does canceling something help?
Well, if there is this
Just
one
one
task
task.
that,
Mm,
that takes half of the buffer,
mm.
right?
Yeah. That makes sense.
That being said, if the trashing already started, even if you cancel that thing, the trashing will still, will keep going for some time. Like you will need to refill the
Maybe.
buffer, the caches and whatnot,
To
right?
better
So,
understand how different types of queries impact the buffer pool, we set up a MySQL with a 512 megabyte buffer pool and populated it with 2 gigabyte of data. We executed two categories of queries: lightweight operations, point select and row update queries, each consuming only a few kilobytes of buffer pool space, and heavy dump queries, which use roughly 2 gigabytes of buffer space, the entire data space. We tested the impact of dump query under three workload scenarios: baseline with no heavy dump queries, adding heavy queries at a ratio of 1 in 100K, and the third scenario increasing this ratio to 1 in 10K.
mhm.
Wow, we are really talking about elephants here. The entire data space. Figure 2 shows the performance results in the three workloads. Even a small number of heavy dump queries reduced the maximum throughput from approximately 25 kilo QPS queries per second in the baseline to around 18 kilo QPS with a 0.001% dump query and around 12 kilo QPS with almost less than half with 0.01% dump
Mhm.
query. One in 10,000.
Yep.
Furthermore, tail latency increased sharply and at much lower overall load levels when dump queries were introduced. While such dump queries are rare in typical workloads, our results clearly show that even a tiny proportion can severely degrade performance when the buffer pool is already nearing saturation. The key takeaway is that during heavy load periods, resource-intensive dump queries should ideally be delayed until the system returns to less loaded state. Yeah,
Yeah. Well, here is the thing, right? This dump query
yeah,
by definition uses all of the resources,
yeah.
right? Because it needs 2 gigabyte of buffer space for a buffer of 512 megabytes. So by definition, it will use all of it.
Mhm.
So like by definition, there may not be a good time to run this query.
Yeah. Oh, I guess. Mhm. That's a good.
right? That's the figure, right?
Yeah,
No,
performance.
no, this is figure 3, and this one is figure 2. That's on the previous
Oh,
page.
yeah. Figure two, impact of dump queries on buffer pool contention. Let's check. No dump. 0.01 dump. Okay, half the throughput. P99 latency. No dump. Okay. Oh,
Mm.
sure.
Okay, yeah. So the red and blue line, when the load is small, right? They're kind of the same. Like
Yeah.
there is so I guess, even though it uses all of that buffer space, when the load is very little,
Yeah.
it can sustain that thrashing okay-ish. The latency is still higher, right? Because obviously it's still thrashing, it's still doing more disk stuff, but the throughput is not
Correct.
impacted. So yeah, like you know, just looking at the latency again, like because this takes all the resources, right? There is just like you know not really a good time ever to run this type of task.
Mhm. Mhm. Okay, buffer pool contention occurs independently of the overall system memory pressure. The buffer pool is configured to be smaller than the total system memory. Therefore, monitoring overall system memory usage alone is insufficient to detect or
Mhm.
mitigate buffer pool contention effectively.
Yeah.
Two, table lock overload. Go ahead.
Okay, so table lock overload. MySQL uses table locks to manage concurrent table access. Typically, these locks are efficiently managed, but complex interactions among requests can sometimes cause locks to be held longer than necessary, and thus exacerbate the lock contention. For example, MySQL backup query acquires write logs on all tables before obtaining the necessary metadata logs. The
Mhm.
backup query normally holds these logs very short, with little disruption. However, due to some subtle interactions, a long-running table scan query can cause the backup query to hold the table logs much longer than intended and prevent MySQL from processing subsequent write queries.
Hmm,
Okay,
interesting. So
some
it's
subtle interactions. I wonder, a little bit more about what these interactions are, but yeah.
it acquires write logs on all tables before obtaining necessary metadata logs.
Mhm.
But yeah, this already looks troublesome. And then normally this is supposed to be short, but due to subtle interactions, it's longer. Interesting. Okay, to demonstrate this scenario, we reproduced the backup query overload issue using a database containing 5 tables, each with 1 million rows. We ran two types of queries, long-running table scan query and lightweight operations. As before, specifically, we executed a mixed workload primarily consisting of lightweight operations and introduced one scan query at 5, 10, and 15 seconds and launched a single backup query at 20 seconds. As figure 3 shows, under lock contention, MySQL end-to-end throughput dropped sharply to around 11 kilo QPS. When we remove the backup query or the table scan queries, the throughput restores to approximately 25 kilo QPS. This case shows how a single problematic request can significantly impact overall system performance. Yeah, it's single, but it was
Mhm.
like elephant. Call it an elephant, right? Call it a whale.
Yeah, yeah.
It's the whale of a uh, query.
Well, in this case, it's actually not a single, like it's an interaction of two, elephants, right?
Hmm,
Because like a table scan is not a cheap operation. It's definitely like cheaper than probably a backup of all tables, right? But it's
hmm,
still not a cheap operation.
mhm, mhm. What is going on in figure 3? Performance impact of table lock contention. Lock contention runs both scan queries and the backup thread. Drop scan represents workloads without scan queries. Drop backup. Oh, workloads with the backup without the backup thread.
Yeah, so the red line shows
Scan
that.
and backup is the lock contention. Red thing, when you delete one, oh, we are so good when you
Mhm.
delete one.
Either one, really.
Other one, of course, these are two whales and just, yeah, with one you can do. Uh-huh. I guess they arrange it so that with one, still, yeah, I mean, sure. Uh,
Yeah, well,
come on.
it's a locking issue, right? So,
Yeah.
um, and the actual workload is a bright workload.
So this is a luck contention issue.
Yeah, yeah. It's not because these whales use like a lot of CPU or RAM or whatnot. It's
Mm.
just locking.
These two cases highlight that small number of problematic requests can have a severe impact on system overall performance. Such problematic requests can significantly reduce maximum throughput, dramatically increase tail latency, and even cause system stalls. Dropping non-problematic requests can temporarily preserve SLO attainment, but cannot effectively resolve the underlying performance interference caused by the problematic request. Sure. Are we going too slow?
Yeah.
Okay.
Limitations of existing solutions. Traditional overload control mechanisms keep track of global signals such as queue lengths to adjust the admitted workload. However, these signals are ineffective in managing the application resource overload, whose severity depends heavily on the application-specific logic. Application resources are logic abstractions managed by applications and thus invisible to the system. For example, Breakwater predicts queuing delays for incoming requests based on past observations, but it cannot directly associate the global queuing delay with contention on a specific resource, such as MySQL buffer pool contention.
Mhm.
Without knowing in advance which requests will monopolize critical resources, Breakwater is unable to accurately identify and drop problematic requests.
What the hell kind of a name is Breakwater?
Uh, Protego allows requests to execute normally. It dynamically detects lock contention and drops requests during execution. However, Protego only monitors each request's locking delay and drop requests whose lock wait times are approaching SLO violations. In other words, it cancels requests that are victims of lock contention rather than identifying and canceling the request causing the contention. Consequently, Protocol often treats symptoms rather than addressing the root cause and thus is ineffective in mitigating application resource contention.
Another potential solution is performance isolation. We talked about this, right?
Mm-hmm.
State-of-the-art systems such as Pbox do not rely on static quota but dynamically adjust resource allocations based on observed request performance. It estimates resource users. Okay, however, such performance isolation mechanisms do not drop running requests. Therefore, while isolation proactively manages resource allocation, it cannot directly mitigate resource overload caused by the problematic request already execution. Okay. We demonstrate these limitations by evaluating existing overload control and performance isolation techniques using the table lock overload scenario mm, that we just discussed. Figure 4 compares the normalized throughput, tail latency, and request drop rate of Protego, Pbox, and Atropos. I mean, the paper is so straightforward, it hurts. Nice. Right? So you can't argue against it. It says, okay, here is two things we tried, and we see contention. They are contending good, and this is the existing two approaches. We are going to retry them on the contention cases that we have, and show you what happens. Like
Yeah.
uh, protocol successfully bounced tail latency by dropping requests experiencing excessive log contention. However, because it does not specifically target the problematic backup request, it must drop many non-problematic requests, significantly reducing throughput and increasing the overall drop rate. Pbox partially mitigates resource overload by reallocating contented application resources, but since it cannot drop the problematic request that already holds critical resource, it fails to. Okay, let's look at figure 4. Protego, P-Bugs, and Atropos. Oh, Atropos is also here. Protego was the dropping one? No, P.
Protego and Pbox are just
Yes,
two
yes.
different, yeah.
But Protego is the dropping one. P-Bugs is the containing one, basically.
Mm-hmm.
Okay, Protego and P-Bugs, they almost overlap. No, normal P99 latency. Of course, P-Bugs has a lot because it doesn't cancel anything.
Yeah, like, note it's a log scale here.
Wow. And pbox cancels. It has less because I guess it's canceling the things that are waiting a lot. So
Mhm.
of course it has good P99, but if you look at the drop rate, oh yeah,
Yeah.
its drop rate is much higher.
Mhm.
Okay, it's beautiful graph, right? In three graphs we can see the entire thing.
Again, log scale, right? So it may be confusing to people. Like even small difference that,
Mhm,
like
yeah.
you can clearly say, oh, pbox sucks, right? Even if you don't pay attention to like log scale. But then I could say, oh, Atropos is very close to this Protego. But then again, because it's a log scale, that very close is not
Mhm,
really that close.
mhm, mhm. Yeah, yeah. You are mentioning this gap.
Yeah.
Okay. Language applications supporting cancel with initiator. Beautiful. See table one. Another beautiful figure.
Um,
And
okay.
it's interesting that C++ 49 out of 60 supporting cancel with initiator. What was the initiator thing again? It helps you cancel.
Uh, yeah, yeah.
Okay. Prevalence of task. Oh, did we read this
No,
part?
I don't think so.
Challenges. Since the behavior
Challenges, yeah.
individual request on application resource is highly variable and difficult to predict in advance, existing mechanisms inevitably misclassify problematic requests and allow them to execute. An effective overload control system should allow requests to execute first, observe their actual impact, estimate each request's current and future resource usage, and selectively cancel those that monopolize critical resources. Such selective cancellation is key to maintaining SLO while keeping the drop rate low. What are we reading?
Yeah. While dropping and running request helps more effectively mitigate resource overload, this action also changes the application's execution logic and risks introducing dangerous side effects. For example, naively killing the backup thread while it's actively backing up tables could leave the database in an inconsistent state, where some tables are backed up and others are not, requiring developers to significantly change their application code to accommodate an overload control solution for drop and running requests can incur high manual effort and be error prone.
Okay, how do
Uh,
they solve this problem?
yeah, and obviously it's just one example, right? Like you cannot go and like, just identify them that easily, right?
But yeah, let's watch
Mm.
if they are going to mention a solution to this problem.
Okay, prevalence of task cancellation. So here they talk about this table one. Should we skip for the sake of time or?
No, let's cancel preserve and tense. Whenever user task consolation has become an. I mean, this is a foreign topic to us, so I think we should get the background. We observe a program, many of which now provide built-in cancellation construct. What is built-in cancellation constructs?
Again, you can cancel the entire like request flow.
For example, Go offers context package. Did you know about this package, Alex?
Yeah, I use it all the time.
Oh, really? What do you use it for?
I mean, it's almost like a standard thing to use for request response systems written in Go.
Ah, I see.
Yeah.
Where canceling a parent context automatically cancels all dependent work. Nice. Okay.
Mhm.
Similar.
You can set the deadlines and timeouts and like nested timeouts. So you can have like, you can say that, I expect this task to be done in, this much time, put a like cancellation deadline. And then your task creates like subtasks. You can have like a nested smaller deadlines and so on and so forth.
Mhm. Similarly, Java supports threads interrupts, C Sharp provides cancellation token, and C++20 provides stop token. Many libraries and OSs also provide cancel APIs. pthread cancel in pthread library.
The pthread cancel system call in Linux and the cancel IOX Win32 API. These mechanisms provide a strong foundation for implementing safe task cancellation. Application developers often use this.
This paragraph, I didn't. I mean, okay, it said application developers, so maybe let's read that. Tail owns such customization are typically explained. Okay, then it's not saying much. Set a cancellation flag where a cancellation request is issued. Where it is safe to check this flag.
Mhm.
Hmm. So the application writers says that, like in the previous example, it's not safe to cancel the backup now, but when it comes to a checkpoint,
Uh,
it's safe to cancel. Is this what it's saying?
Well, honestly, in terms of backup, I don't know, right? Because like what is safe would be defined by the application,
Yeah.
or right. So,
And it's like
uh,
these application writers are
yeah,
doing a
yeah,
good job of
yeah,
providing that.
yeah,
Okay.
yeah. So like if you're backing up a database, right, and your concern is you didn't back up all the tables, well, then the safety for you is to just finish the entire thing off, right? That means you cannot cancel it. But then what if it runs forever, right? So you need to cancel it. So like the safety here is very
Mhm.
loosely defined, I think.
Because developers explicitly exclude unsafe operations from being cancelable,
Hmm. Yeah.
these customers mechanisms are generally safe. To understand how prevalent customized cancellation 151 from GitHub and GitLab applications were selected based on popularity metrics.
Such as number of stars for each application manually reviewed, its documentation, development logs, user manuals, and source code. If an application exposed to general purpose cancellation API along with corresponding implementation, we categorized it as supports and task cancellation. So that table one you looked at before summarizes the results. We found that majority of our studied applications implement task cancellation within their code bases. Among these, 95% rely on developers to manually decide when and where cancellations can be safely performed. Applications that do not support cancellation are typically non-interactive systems such as libraries or simple single-threaded key value stores where cancellation is unnecessary. Based on these findings, rather than re-implementing generic cancellation mechanism, from scratch, Atropos leverages each application's existing cancellation support to ensure safety and consistency.
Okay,
So, so,
design
so
proposed.
they're pretty much saying that they will slot into like the application's way to cancel things, right? If something is
Yeah.
cancelable, then it's cancelable. If something is not cancelable, even if it consumes a ton of resources, you're out of luck.
But remember, they had two metrics that they maintained, like the contention level and how much resource would be freed if this is canceled. I guess they are adding that themselves to the applications. So they are changing the applications, right?
I guess.
They need to be adding that themselves. Okay, let's look at three design of Atropos. In 3.1, integrating Atropos to applications. Example of tracing buffer pool in MySQL. I guess they are adding
Mm-hmm.
these instrumentations, triggering cancellation, uh, algorithm one, implementation. Come on. Describing 16 real-world application resource overload cases that we reproduce. MySQL, Apache.
Maybe they actually refer to Apache Web Server.
It could be. Yeah, yeah. Elasticsearch, Solr, etcd. Complex read query blocks other queries. Interesting. What is a complex read query in etcd? It blocks other. Wow. Wow, who knows? Evaluated software and integration effort measured by added lines of code. So they add
Mm-hmm. I
instrumentation.
mean, it's reasonable, right?
Reasonable, yeah. And with LLMs, you can know where to add. You can be technically fearless with LLMs. Normalized throughput. Nice. I mean, yeah, you can see this is a strong systems paper.
LLMs are
Forward.
stupid. I have something that's completely off topic for you though, but
Go
they're
ahead.
so stupid.
Mhm.
I was troubleshooting why my computer died yesterday,
Hmm.
and I asked if a particular clicking noise is okay, like when the power supply starts up,
Mhm.
and this is what LLM told me. Um, um, A single click at startup is usually normal for computer's power supply unit, often from an inrush current bypass relay. I don't even know if this thing is real, inrush
Hmm.
current bypass relay, whatever that is, right? If the clicking is rapid and accompanied by computer failing to start, it typically indicates a problem with the car battery, a starter motor, or other electrical issues.
Car battery.
A starter motor.
Okay. Yeah. Okay. But you did ask an LLM. So they already won. Figure 10.
Actually, I didn't. I Googled, okay? It was unsolicited.
That doesn't count. Ask ChatGPT or Gemini. Go to Gemini.
What does Google do in their search?
I think that's not Gemini. I
I
think
think
that's
it is.
watered down. SLO maintenance under different thresholds. Overload of Atropos. Overhead of Atropos. It's cool. This is open source, or well, they don't have much, right? They just say the detection, I guess, that instrumentation could be a small library that they give, but then you do it with this, and the algorithm is there. Okay, conclusion. Yep. Application level resource contention is inevitable in highly concurrent software. We propose a novel overload control approach that leverages built-in task cancellation support. Now, we implement this approach in framework Atropos. Slotin, while it demonstrates that targeted cancellation is a powerful and generous strategy for overload control, it's available here. Okay.
Here is the thing, right? At the big level, right?
Mhm.
Um, they are not solving the problem of identifying an overload, right? Existing approaches do that just fine, right? So they are solving the problem of what task to kill for
Yeah.
the maximum, bang for your buck, so to speak,
Mhm.
right? So
Yeah.
killing what will, improve the situation the most.
Yeah.
And they approach this from the perspective of essentially monitoring the resources, right? The logical resources, like how
Mhm.
much the buffer it uses or how many locks it acquires, right?
Yeah.
So and that monitoring of these logical resources is what the instrumentation is for,
Yep.
right?
Mhm.
So yeah.
Yeah, it's straightforward. Let's read this, maybe get some idea.
Mhm.
I think we got the idea. After we understand more, we can stop basically. We present Atropos, an overload control system that selectively cancels requests responsible for monopolizing application resources and causing an overload. Directly track application resource usage and use this information to guide cancellation decisions. Unlike traditional overload mechanisms that react only end-to-end performance signals, Atropos proactively monitors the resource impact of each. Yes, this is the key. Admitted request and cancels those most likely to cause performance degradation. How hard is it to do this for a big database like MongoDB?
I don't think we should discuss that on a video.
No. Well, okay. Well, they did it for Postgres and MySQL,
Yeah, yeah.
so it's not that hard.
Mhm.
Let's see how they did it. But this is the key, right? This is the key contribution, basically. And since they did it for Postgres and MySQL, it shouldn't be that hard. Figure 5 shows the high-level architecture of Atropos. Developers first use Atropos APIs to identify and register user requests and internal background tasks as cancelable tasks. Okay,
So figure 5.
here is figure 5. Okay, request, application, task, background, task. Built-in cancellation. Where is Atropos? Okay, there it is.
Mm,
Atropos Runtime Manager, per task resource usage. Atropos Estimator.
mm.
Is this using AI?
Yeah.
Three contention
It would
rules.
have been an abstract or intro if it.
Yeah, yeah, we would have known. Policy. and building cancellation. Okay, it's going to talk about runtime manager in 3.1 and 3.2, estimator 3.4. What is 3.3 then? Policy 3.5, dropping 3.6.
Mhm.
Interesting. How does it know like this is disk and this is using that much this much disk. This is using this much CPU. How does it track CPU?
Well, again, like the CPU would be hard,
Hmm.
right? But you can track the runtime, just how long you
Hmm.
do something, right?
Okay, so you should get a signal every time it's suspended, every time it
Yeah,
gets back up.
yeah. I mean, yeah, ideally. But for the examples that they had, like this buffer pool, right? It directly, interacts to this buffer, so it knows exactly how much of that buffer it needs, how much memory it tries to like use from cache or put to cache, right? The same with logs. Like each task should know exactly how many logs it needs to acquire and things like that.
Yeah.
Right.
Okay.
So yeah, the CPU may be like more interesting. Um, um, Disk I/O, like IOPS or bandwidth,
How about network?
yeah, like estimating those like physical resources would be, I think, more like a bigger challenge. Let's see if they talk about it.
Okay, at runtime, the Atropos runtime manager 3.2 tracks resource used for each cancelable task.
Mm.
When the overload detection module observes that end-to-end performance violates SLO, it activates the Atropos estimator.
The estimator then analyzes the resource usage information provided by the runtime manager and computes two critical metrics: resource gain and contention level, step 2 and 3. These metrics quantify current resource contention and predict the potential performance improvement achievable by canceling specific tasks. Next, the policy engine 3.5 uses these metrics to decide which tasks to cancel. So I guess it's some kind of scoring system, right? Based on those two metrics.
Yep.
It selects an optimal task by balancing the severity of resource contention and the potential resource gain from cancellation across multiple resources. Finally, Atropos triggers the selected task's built-in cancellation mechanism to safely terminate execution.
Oops.
Integrating Atropos into applications. Figure 6a lists the APIs used to integrate Atropos into an application. At its core, Atropos treats all application tasks uniformly through an abstraction called cancelable task. A cancelable task represents a logical unit of work within an application, such as a user-issued database transaction, background operations, such as garbage collection or deadlock detection, or groups of requests sent from a single user. Developers decide how application tasks should be aggregated into cancelable tasks. For example, they can either group all requests from a single user into one cancelable task. Oh, okay. Kill everything from a
Yep.
user. Or treat each request as a separate
Right,
cancelable task.
because sometimes if you kill one thing from a user, it makes the others obsolete anyway. So for that, you want
Yeah.
group.
But I think it's all like developer decided, right? Like it's
Yes,
how you use the system.
exactly. Exactly.
The create cancel and free cancel APIs define the scope of cancelable tasks. When registering a task via create cancel, developers may optionally provide a unique key to explicitly identify the task. If
Hmm.
unique key is not provided, Atropos, there is a picture, generates a unique key automatically. To facilitate safe cancellation, developers must specify application's cancellation initiator by providing a function pointer to Atropos through the setCancel initiator. Atropos calls this registered callback function when it decides to cancel a task.
Hmm.
6 point something was the API, right? Oh, that's a listing, right? Figure 6. Okay.
Hmm.
What are these APIs? Main APIs, cancelable. Okay, free cancel, set cancel action.
Oh, you want to go to figure six?
Yeah, I'm trying to understand what they do.
Mm.
Per task application resource usage, get resource, free resource, slow by resource. So this like B API for tracking per task application resource usage.
Yeah.
right? So I guess get resources when you request some resource, free resources when you're done with this resource. So I'm not sure it can track things like CPU.
Yeah, interesting. Should we search for CPU? Uh, CPU is mentioned in page 6 for system resources such as CPU or network. In 3.2, it says Atropos can monitor usage by using existing tools like C groups and attributing resource consumption to the threads executing each task. However, application resources are much harder to trace because their usage patterns are deeply tied to application-specific logic. For example, a queue may be used for task scheduling in one application and for message passing in another. These variations mean that application resources lack standardized hookup interfaces. Blindly instrumenting all possible usage points would introduce significant overhead. Atropos addresses this challenge by unifying all resources under a single abstraction, the application resource. I don't get it, so we should read it.
Well, you pretty much read it because we were done with 3.1. We had like one paragraph. Yeah.
Let's read it proper here. I read this part. I read this
Yeah.
paragraph.
So should we look at figure 7 that shows how MySQL, a widely used database system, integrates with
Okay,
Atropos, or we can skip that?
let's look at it. Where is it? Okay, that's it.
Yeah, so figure 7,
Mm-hmm.
um,
Great, cancel, free cancelable C.
set cancel action.
Yeah.
Where do they?
I think that's where do they kill it? I think that's
That's
later,
the killing
3.6.
and tracking the resources is figure 8.
Okay. Oh, I thought for killing you call the initiator task.
So
Killing
figure
like
7 is
yeah.
setting the cancellation, right? It's set cancel action, SQL kill. That's the cancel action.
And figure 8 is tracing buffer pool. It's
Yes,
not
figure 8 is get resource, right? When
killing
you
will come later, I think.
so,
Triggering.
so in figure 8, can you go back to figure 8 for a sec?
But that's still not killing.
No, it's not killing, it's tracking the resources,
Yeah.
right? So um,
Yeah. Get resource slow by resource. Free memory. What is
so
slow by resource?
I think that's your that I don't know.
Ah.
Low by resource records when a task is delayed while waiting for a resource.
Hmm.
Okay, that's in 3.2. I guess we can read the 3.2 now.
Okay, let's read the rest. Atropos addresses this challenge by unifying all resources under a single abstraction, the application resource. How does that help? Each application resource supports three operations: get, free, and wait. To capture these operations, Atropos provides three resource tracing APIs shown in figure 6b. Get resource, free resource, and slow by resource.
Yeah. Get resource API records when a task acquires a resource. Free resource records when a resource is released, and slow by resource records when a task is delayed while waiting for a resource.
Yeah, and how does this apply to CPU?
I don't think it does. That's the thing, because you cannot say that I'm about to use this much CPU and then like the CPU, network bandwidth, disk bandwidth, right?
Maybe it's
These are
estimating.
not replenishable resources, right? Like they're instantaneous resources.
I mean, maybe it's estimating it through the threads. I don't know. Through when those threads are, when the
Maybe.
system threads are active for that.
But see, like in that sense, get resource, for example, then we'll say get resource, I don't know, 1%, right? Or one. We'll say that I am going to use 1% of the CPU, right? For this task, which is like very hard to estimate on a like a per task basis.
Each API takes two parameters: value, which specifies the resource being acquired, released, or waited on; resource type, which specifies the resource type. Okay, here is our answer. Currently, Atropos supports three categories of application resources.
Synchronization resources represents resources protected by synchronization primitives. Queue resources represents an application managed task queues, and memory resources represents an application managed memory pools or caches. This unified abstraction allows Atropos to handle different types of resource contention consistently. Equally important, it enables incremental extensions to support new resource types without requiring changes to the core framework.
Does the network fall under synchronization resources?
No, they're talking about locks,
Resources?
Murat. Not
Queue?
like, so synchronization resources are locks, mutexes.
Yeah. How about queue resources? Does the network fall under queue resources?
It's application managed task queues,
Yeah.
right? And memory is application managed memory pools or caches, right?
Hmm.
So not OS managed, not, yeah, application managed.
Hmm. Interesting. So no CPU or network or anything. But here it says for system resources such as CPU or network, it can monitor by existing tools like cgroups and oh, it says this is easy. And we are talking about the hard part about application specific logic next.
Yeah, but again, it's not easy, right? Because again, like in languages that they target, some of them, like in Go, right? There are no threads. There are
Mm.
Go routines, right? Like you cannot just look at the system thread in the Go process and say, oh, that's that, right?
Yeah.
Um, like keeping track of the CPU usage on a like Go routine is very, very hard.
Mhm. Got it. Okay. The three APIs are straightforward to instrument. Figure 8 shows how MySQL uses these APIs to report buffer pool usage in case 1. When a request acquires a new buffer page from buffer pool, it calls buff page getGen to return a pointer to the new page. The get resource API is invoked just before returning the page to record the get operation. If MySQL cannot obtain a free buffer page, it calls buff LRU scan and free block to evict a dirty page. In this case, the slow by resource API is placed immediately after the eviction function to capture the delay. Finally, when the request releases a buffer page through buff LRU free, the free resource API is invoked to record the release operation.
Oh,
Mm,
see, this slow by resource is you telling Atropos that you are slowed down by this resource,
yeah, interesting.
right? So again, like you need to be very careful in the instrumentation.
Yep. Yeah, not straightforward. Atropos ensures that its resource usage tracking works correctly with common system optimizations such as batching and asynchronous processing. For batching, Atropos attributes the resources consumed by each individual request within a batch. The overhead of each API is minimal as Atropos only records a tuple along with timestamp. We use RDTSC instruction to measure CPU cycles. What is RDTSC? Let me check. Real-time stamp counter.
It's just a clock.
X86 reads a 64-bit counter that increments roughly every processor clocks. Oh, from the clock, it can see how long we used the CPU. Hmm.
Yeah, that's what I said like before. They most likely just need to count like how many like how long have you been executed?
Yeah, yeah. I think Barish did previously some
Mhm.
side channel detection, so he knows how to use these low-level counters to get information about execution. This must have looked easy to him
But
because
again, that's not them recording the CPU as the resource. That's just them, uh, counting
yeah,
other things, right? It's like slow down. So what is it? I kind of missed it.
no,
Yeah,
here it's saying
yeah. The
he.
resource usage tracking works correctly with common system optimizations, right?
Mhm.
Uh,
For every event, instead of recording a timestamp for every event, Atropos samples timestamp at fixed intervals and assigns the same timestamp to all events within that interval. While this batching approach reduces timestamp precision, it is sufficient to detect tasks that monopolize resources. To improve accuracy when needed, Atropos dynamically switches to record the timestamps for every event when the detection model detects a potential overload. Okay. Triggering cancellation.
Atropos has an overload detection module that periodically monitors the software's end-to-end performance to detect resource overload and trigger cancellation decision. As shown in our case study 2.1, resource overload often exhibits patterns similar to regular overload. Thus, Atropos detection module leverages the state-of-the-art overload detection method, TAN. Specifically, it continuously monitors application throughput and latency. Okay, yeah. When latency exceeds the service level objective while throughput remains flat, this indicates a potential resource overload. In such cases, the detection agent notifies Atropos estimator, which then verifies whether a specific application resource is the bottleneck. If a bottleneck resource is confirmed, the estimator classifies it as a resource overload and triggers a cancellation decision. Otherwise, the performance degradation is classified as regular overload.
Yes. What
So,
is?
regular overload is like, we're out of CPU kind of overload,
Mhm,
out of disk IOPS, bandwidth, network.
mhm,
Because remember, they only deal with the logical resources, the application level, like logical resources.
hmm. And these are locks, queues, and what was the other
So
one?
they have locks, queues, and buffers.
Buffers. What is this then? State-of-the-art overload detection method. What is this state-of-the-art overload detection method?
Overload control for microscale RPCs with breakwater. SOSP, no,
Oh,
OSDI 20. Yeah.
interesting. Okay, estimating resource overload. Contention level resource gain. Below we detail how Astropos calculates these metrics for the three supported application resource types. Memory-related resources. Alex, can you read?
Where we are.
Here at the top.
Okay. Yeah. Memory-related resources. Intuitively, buffer pool contention reflects how often queries must evict existing pages to make room for new ones. The more frequently evictions occur, the higher the contention, since queries compete aggressively for limited buffer space. For example, in case 1, section 2.1, suppose that query I acquires MI buffer pages from the buffer pool, releases FI pages, and consumes EI evictions during a certain interval. The buffer pool contention level can be computed as the average eviction ratio of sum of EIs over the sum of MIs, right? So MI is acquisitions, right? And
What is EI? It didn't talk about EI. It talked about really causes.
EEI, evictions, right? So
Mhm.
essentially, yeah, how many
Yeah.
evictions over the total things you need, right?
Uh-huh.
Mm.
Mhm. What type
Um,
of propose runtime manager?
as shown in figure A, the number of pages acquired corresponds directly to the number of get resource API calls in the buffer pool, while the number of evictions corresponds to the number of slow by resource API call. Both are traced by Atropos runtime manager. Defining resource gain for memory resources is challenging. Intuitively, it could be defined as the number of buffer pages held by a request expresses mi minus fi, since canceling the request would immediately free those pages. However, this definition only captures the memory released at the moment of cancellation and does not reflect the true benefit of dropping the request. For example, consider two requests that both monopolize the buffer pool. Query A has completed 90% of its workload, while query B has completed only 10%. Although query A holds more buffer pages than query B, canceling this nearly finished query would bring less performance benefit than canceling query B. We had this question before, right? Like, do you really want to cancel like things and waste a lot of resources? To make matters worse, because query B is just beginning, even if query A were canceled and its buffer page is freed, query B would eventually monopolize the buffer pool again. Thus, measuring resource gain by current memory usage incorrectly biases the decision towards long-running tasks that are close to completion, rather than the tasks that still have substantial memory demand ahead. Okay.
Interesting.
I mean, it makes sense, right? Like you want to.
But then how do they kill
Yeah.
the ones that have substantial memory demand ahead? And
Next paragraph. We instead
uh-huh.
define resource gain as the future memory usage of a task.
Oh, what is S?
Yeah, I don't know, as something. Yeah.
Yeah, this
To
is
estimate future usage, Atropos assumes that a task's remaining resource demand is proportional to its remaining workload. Okay, how do they know the remaining workload? Under this model, the resource gain is calculated as the current resource usage multiplied by progress, expressed as mi minus fa times y minus progress I over progress I.
to
Okay,
estimate. Okay, go ahead.
yeah. To estimate task progress, Atropos employs the well-established get next model 20, which define progress as, should we look at 20?
After this paragraph,
Okay, which defines progress as prog I is k over n, where k is the number of rows already processed by the operator, and n is the total number of rows expected by completion. Okay, so that was my question, right? Like they are becoming like database biased, right? Like it
Yeah,
has to be a database system that has some way to essentially give you like that query plan information, the cardinality of what you scan and things like
that
that.
also they also look at Apache, Apache web server. So
And etcd
and etcd.
and Solr, which is like a search. So I don't know.
And for memory related, they also qualify. Oh, keep reading. This model is suited for with quantified progress information such as databases and search engines. For example, MySQL has the internal variable rows examined, which records the number of rows processed by request, and the variable estimated rows, which stores optimizer's estimate of the total rows to be proposed. But this is database specific. What do we
Yeah.
do with the others? What is then the resource gain for the others? Atropos can read these values for each request to obtain an accurate progress information. I think they make it application specific, so to speak. And
For
maybe
applications without such metrics, Atropos provides an API that allows developers to explicitly support
ah,
accurate progress estimation. So they
oh,
say,
how? Like how?
not my problem. You deal with it.
How do they
Yeah.
deal with it for
Yeah.
Apache or Solar or etcd?
I mean, for Solr, maybe, right? You have like a set of things you need to scan through, you're going through some of them. Like there is probably like a progress, right? But yeah, like,
Okay,
yeah.
no, let's keep going. While the proportional assumption is strong and may be inaccurate for many resources, it remains. But I like that it solved the problem of not not killing a task that's already made a lot of progress,
Mhm.
but estimating that this next thing is also a whale and it hasn't started. Let me kill that. And
Yeah. Yeah,
this.
that's nice.
While the proportional assumption is strong and may be inaccurate for many resources, it remains a valid and effective choice in the context of cancellation, first building and the current. I will skim it. Okay, we can go to synchronization resource.
For resources protected by synchronization, primitive's contention can be defined as the ratio of the time requests spend waiting to acquire the resource compared to the time they spend actually using it. Right.
Nice.
So that's when they need like those, uh, high precision clocks, right? And also like lightweight, in terms of mm, resource usage itself. Um, if the waiting time dominates the total execution time, it indicates that multiple requests are blocked and the resource is overloaded. Consider the table lock in MySQL as an example. Suppose a write request I monopolizes the table for I EI, EI seconds, while multiple read requests J each access the table for EJ seconds. The contention level can be expressed as EI times J over the sum of all EJ.
Let's skim a bit.
Uh,
Resource gain is defined as oh, key resource is one paragraph.
hmm.
The resource gain is defined as the amount of time as the request holds the resource. Why? But shouldn't this be again feature looking? Why are you
Well,
not?
yeah, they look at this progress again, right?
How?
Remaining workload fraction.
Oh,
So it still looks at
where? How do we look at it? I don't get
the
it.
resource gain is defined as the amount of time a request holds the resource. Similar to memory resources, this metric is defined in terms of the future resource holding time. It is calculated as the current holding time multiplied by the remaining workload fraction.
Okay, it's coming next. Okay, I see. For example, if I write, okay, nice. Okay, cool.
Mm.
Simple ideas, but very powerful ideas. I like it. And it's like very straightforward work and with the
Mhm.
evaluation strong. Queue resource. The contention level for queue resources is defined as the ratio of the time requests spent waiting in the queue to the time they spent executing after leaving the queue. Interesting. Right? So if you
Mm.
spend more time at the queue, this is the contention level for queue resources. Oh, queue-based resources, basically. That's what queue resources
Yeah.
mean. A higher ratio indicates more severe contention as the task wait longer than they run. For example, if a request waits in a task queue for an average of 1 second but takes only 0.1 seconds to execute, the contention level is 10. The resource gain for a queue resource is defined as the expected future thread time a task will consume. What does this mean, Alex? Future, I get it. What is
Yeah,
future thread time?
essentially the time in a queue. I don't know.
Why do they call thread time a task? Oh, no, thread time is, yeah, time for the queue resource, something that you are waiting. That would be the resource gain.
Mm.
And if this is going to consume a lot of time at that thread, you kill this. But how do you know? This is hard to identify, and there is no hint here.
Mhm.
Do they leave this to the developer?
Again, I guess they can still look at this, progress thing that they did, right? Like, and how much remaining versus how much, they already took. And
How do you know how many times you will get to have the thread?
Mm.
How do you know the number of iterations you will go through the loop?
Mm.
Interesting. Multi-objective cancellation policy. Shall we skip this?
So that's how they decide what to cancel, right?
Yeah.
Mm.
Algorithm 1, statistics of each cancelable task, resources map, statistics of each resource. Find the dominator tasks. Find the optimal task to cancel. For task in dominator task, do total gain 0. For resource in resource map, do content level, get content level, gain, total gain. If total gain greater than max gain, then max gain is total gain. Best task.
Find the dominator task.
Yeah, sure.
What is the dominator task, right? Well,
The heavy tests. It doesn't say dominator task. It says dominator
dominated
task.
tasks. It's plural, right? So
And among
I think this would be the tasks. Okay, yeah, I don't know.
and maybe this is across the three categories or something. And then you look at among them. Let's see if it is by three categories.
You know, I searched for dominator and
Hmm.
it appears 3 times in the paper, all of that in the algorithm.
Okay, maybe let's read a bit about this, okay?
After Atropos estimator computes contention level for each resource and the resource gain for each task resource pair, Atropos must select the request whose cancellation gains the largest performance benefit. A simple policy is to cancel the task with the greatest resource gain on the most contended resource. However, this policy assumes that resource gain from different resources contribute equally to performance improvement. In real-world application, the performance impact of different resources is not directly comparable. For example, a buffer's pool contention level is the eviction ratio, while a table's log's contention level is the log's weights in time. Even if both report the same numeric value, like 20%, the implications are very different. Additionally, the resource overload may occur across multiple resources at the same time. Selecting a task based on the most congested resource might identify one that is optimal for that resource, but some suboptimal overall. For example, suppose that there are two overloaded resources A and B. Task X has resource gain of 3 on A and 0 on B, while task Y has a gain of 2 on A and 2 on B. In such cases, it's difficult to say that canceling task X is better than canceling task Y, since the performance benefit depends on how the resource gains
So
across.
it looks like the dominator task is one from each resource category. Is that right? One from each category.
I don't know. I would look for a dominator resource, the one that is going to bring you the most impact, and then look for a task to kill from that resource.
Right. But it takes the dominator resources, and among them, it finds what is the most benefit.
I don't know. I'm making stuff up. We haven't finished reading it.
Yeah.
Right? Like,
Huh.
to make contention level comparable across different resource types, we normalize contention on a per window basis by expressing it as a fraction of the request execution time lost to a given resource. Let T execution denote the request execution time in the window baseline, and let dr be the contention-induced delay attributed to resource R. We define CR as dr of T exec. For every resources, the delay dr is computed as eviction time weighted by contention level. For synchronization in Q resources, the delay corresponds to the measured waiting time. With the normalized metric, we then question. The next question is how to identify the optimal request for cancellation. Inspired by multi-objective optimization problems, MOOPs, in operations management, we propose multi-objective cancellation policy that evaluates the impact of canceling a task across multiple resources. The key insight is that performance improvement from cancellation is not determined by the single most contended resource. See, that would be my naive approach, right? But by the combined, well, I didn't say the most contended, I said the most impactful, but whatever. But by the combined gains across all resources. Similar to MOOPs, our approach seeks to identify the task whose cancellation gains the largest overall performance benefit across all resources.
Okay, let's go back to the algorithm again. For
No,
test,
we get to the dominated things in the next paragraph. So,
do you want to read it? Can
can you read it?
identify the request that provides the greatest overall performance benefit. We leverage the concept of the non-dominated set from multi-objective optimization. Intuitively, the non-dominated set consists of cancelable tasks whose cancellation brings strictly greater resource gains compared to tasks outside the set. Um, for example, that's interesting. A task that provides 5 units of resource gain in resource A and 2 units of resource gain in resource B clearly dominates another task that provides only 4 units of resource gain in resource A and 1 unit of resource gain in resource B. Atropos identifies all tasks that belong to this non-dominated set. Uh, non-dominated set, isn't it the dominating set? What does non-dominated set mean? Lines 210 of the algorithm 1 outline the process. That's literally the dominator tasks. Why do you call it non-dominated task then? A task is included in non-dominated. It has strictly larger resource gain in at least one resource and is no worse in all. I'm a bit lost. Which task B, task map do if domain task B
Okay,
task.
I think I get the idea at the high level, right? They get a set of tasks that they cannot compare easily, right? So if you know that a task is, well, you can say that one task will be strictly better than another if it performs strictly better on all the resources, right? But then if you cannot compare them, like you find the best of these tasks that you cannot compare, and that creates you
What I don't
that's
understand is like let's say that I mean the resources may not contribute equally.
it,
Maybe one resource is more contented. So getting even small improvement in that resource is more important than getting larger improvement in another resource.
Okay, Murat, let's say you have three resources, A, B, C, right? And you have one task that's like a 3-3-3,
Mhm.
right? And another task that's 4-3-3,
Okay.
right?
No, I
So,
get the dominating idea. I'm
yeah,
just saying that in the second part, when selecting it, how to
it,
then account
yeah,
for
okay,
which
and you have
resource
a
is the bottleneck.
yeah, that's the loop in lines 12 to 20, right? So they get those, top tasks, and then they pick the best one.
What is best? That's my question. Maybe even a small thing on a
That
resource that's more bottlenecked is more important. Oh, they look at the contention levels as well. Contention level is also part of the equation. See, that's beautiful.
Mhm.
Contention level times gain. It becomes a multiplicative factor.
We need to start wrapping up. It's 11 o'clock.
Yeah. Okay. Implementation, addressing fairness issues. Table 2. Um, Evaluation. Normalize P99. Okay, these cases C to 15. The first 5 is MySQL. The next 3 is Postgres,
Mhm.
and so on. Atropos, Protego. Wow. Yeah, it's a big difference. Throughput is more important. Latency, not as big difference there as expected.
Again,
Because
latency is the log scale, Murat.
that's true. But latency doesn't mean much. You could have much better latency by canceling above a threshold.
Yeah.
Uh, you need to look at the throughput to get the full picture. And
Well, they still have low latency, lower
in
than most of the stuff.
MySQL, it provides a lot of improvement. In Postgres, on C8, not as much, right? On the others
Hmm.
are also not that dramatic. Let's look at C8, System I/O. Other queries. And it's basically doing as good as
Yeah.
P-Box.
Okay, one sec.
Mhm. Okay, let's wrap up. Maintaining the SLO under resource overload. Comparison of different cancellation policies, multi-objective versus heuristic versus current usage. Of course, multi-objective is better. That's why you show. But C8, let's look at this case. Yeah. Okay, throughput. Related work. Okay, let's wrap up.
Hmm.
It, it's a really nice systems paper, right?
Yeah, and not to mention of like AI, ML, LLM.
Yeah, for a change. Yeah, that was pretty good. Um, and it has good gains. So what's the big idea? The big idea is to estimate and kill very like sniper, very targeted task cancellation. And in the beginning, I said it sounds too good to be true. It depends on their workloads. Did they use regular workloads or?
Keep in mind, they are not addressing the regular overload, right? It's the overload on these logical resources,
Mm-hmm.
right? So, I think when we had this discussion, too good to be true, we were thinking about like a regular type of overload. You just like give it too much tasks that, you know, more tasks than, you have CPU or more tasks than you have IOPS, right? But I think here it's slightly different, right?
Okay.
You're fixing the problems with locks, right? So you can be very strategic. It's a logical resource. You can unblock a lot of work in a very strategic way. The same with like those like page trashing, right? Caching and whatnot. If you kill the work that causes your caches to go invalid and trash,
Mm-hmm.
then you get like disproportionate benefit.
Mm-hmm.
Right? Versus if it's like a regular overload, you kill a task, well, you only gain as much as the task, for example, use the CPU.
Mm-hmm. Mm-hmm.
Right? But I think here they have like this disproportionate gains because these resources are kind of they're not just like these resources they create like disproportional bottlenecks.
Mm-hmm. Yeah. 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 Oh, a much more interesting paper than I first thought, and I enjoyed it more than I thought. It was,
Mhm.
and the big ideas are not that big ideas, right? So just the contention level and the targeted gain idea, and the algorithms were not that um, complicated, right? Was there any complicated idea in the paper? They referred to a couple previous work, like
Yeah.
10, which turned out to be the breakwater work. Why did they refer to this? They referred to for one thing. I mean, for monitoring, maybe? Why did they refer to this? Do you remember? I forgot.
Mm.
It seems like they offloaded
They,
one,
they refer to it several times, I think.
but they offloaded something to this 10.
Mm. Yeah, it's like
Oh, here.
overload detection, adjust admission based on observed queue and delays.
Mm-hmm. Mm-hmm.
Um, yeah, they say making it effective for CPU and network overload, but ineffective for application level resource overload. Right, so that's the related work says, right? So,
No. Oh, okay.
yeah, but earlier they referred to this still for the reason of like detecting.
Wait. Tell me again. So it says that this is good for normal overload detection, but not logical application level overload
For
detection.
example, breakwater adjusts admission based on observed queue and delay, making it effective for CPU and network overload. So not detecting, but like dealing with that, right? Like
Where do you read this?
that's the related work. We didn't get to it.
Oh, I see.
Yeah.
Okay.
But in earlier they called it the state-of-the-art overload detection method.
Yeah. Hmm. But then they also had a sentence saying that, but this is not good for application level, and they went
Mhm.
into application level detection themselves.
Yeah.
So not much, but it's interesting. They just, I think, the gain came from this abstraction to three resource types and doing it for each of the three. They chose a manageable problem, so to speak,
Mhm.
and made it more controllable. Nice. Who are the authors again? Yeah, it's not hard to do, it seems. Okay, Alexei,
Mhm.
let's stop here. That wasn't too bad, almost 2 hours. And we have a good idea of what they did.